Hello everyone. Now I want to move to a new topic in our fluid mechanics and hydraulic engineering course. So far we mostly covered fluid mechanics, all the principles like principal equations and governing equation for fluids, which are momentum equation, conservation of mass or continuity equation, and also energy equation like Bernoulli and we found Bernoulli from energy equation, and also all the head losses due to friction to that. And also we talked about pipe systems, and now I want to talk about a new topic, which is hydraulic engineering, which is very important for especially civil and environmental engineering applications, where we want to design these open channel flow systems. So let's see what are the open channel flow systems. So here you can see three different open channel flow systems, and as you can see, these are the fluids or flows in which they have a free surface, right? And these are very common, especially in civil and environmental engineering applications. For instance, when you want to design a dam, and then you have rivers or dams, where, for example, for dams where you want to distribute the water, even in the wastewater systems management, these are very important. For farming issues and agriculture, these are very important. And so there are a lot of applications that kind of include these open channel flows and what we call hydraulic engineering systems. Okay, so with this introduction, let's go into some details of these open channel flow systems and see how we tackle the problems in this context. So just note that open channel flows is the chapter 10 of your book, and if you're interested, you can take a look at that. And so one of the specific, so this is an example, or is like a kind of schematic of a channel flow systems in which we are going to go through it. So as you can see, one of the kind of specific properties of these open channel flow systems is that we have a free surface. So the surface here is free, so it can change. So this allows the fluid to choose its free surface location and configuration. So it can change, it can modulate itself based on the topography, based on the gravity, based on the pressure, based on the velocity. So based on all these, based on the friction, surface friction, based on all these factors, the fluid and flow system can kind of adjust itself and change its free surface. And this is unlike pipes. So pipes, in pipe systems, we did not have this one free, I can say one free parameter, right? So in pipe systems, always, all the time, your velocity, your flow, most of the time, I would say most of the time, the flow, the depth of the flow was equal to the diameter of your pipe, right? But here we show, for example, depth of the fluid with y, and it can vary across the channel, across X, and this is unlike the pipes. So in pipes, we did not have this one free parameter. So this is kind of might make the problems a little bit more challenging compared to pipe systems. Okay. So again, we show the fluid depth here as y, which is shown here, and then I want to define some terms here that kind of are common in these systems. And some of these we have already seen, and some of these are new. For example, steadiness, and this was something that we have seen before. And an unsteady open channel flow is a channel flow in which y, which is the depth of the fluid, at a given location, say for example here or anywhere in the system, varies with time or t. So it's a function of time. Okay, this is what we call an unsteady system. And a steady system is a system in which y at fluid depth does not vary with time in this context. Okay, so at any given location, if you look at it at different times, y is constant with respect to time. Okay, it might change with respect to the location. For example, if you go from here to here, here might be a little bit thicker than here, but with respect to time, it is steady. It does not vary with time. If you look at it now and then look at it tomorrow, it's going to be the same. And that is what we call steady flow. But unsteady flow, if you look at it now and if you look at it like a few seconds from now at the given location, you see that the y is going to vary with time. So this is the difference between steady and unsteady flow. And then we also have other kind of definitions. A uniform flow. A uniform flow, which we show it with UF, is a flow in which the depth does not vary along the channel. So if it is your channel, and then your depth, your y, is not gonna change as a function of x or as a function of your along the channel. Okay, so dy over dx here is 0. So this y is constant in space. And that is what we call uniform flow, and I showed it here as UF. Okay. And then the other definition here we have is gradually varying flows. So here I show it here, in which this depth is varying, right? Is changing with time, with location. I'm sorry, but its change is very slow. So dy over dx is greater than 0. It's not equal to 0, but is much smaller than 1. And this means that this flow is varying, but it's varying gradually, very slowly and also this slope is not very steep. It's not a steep slope. Okay. And the other term that I want to define is rapidly varying flows, which we show it with RVF, and you can see an example here in which the fluid depth is varying rapidly with the channel location. So here you have one depth, and then here you have a significant change in the depth. Here you have a significant change in the depth. And in mathematical representation or in mathematical terms, we can say that dy over dx is almost equal to 1. So it's on the order of 1 or greater. So it's changing with channel, along the channel very rapidly. So this is what we call rapidly varying flows. And I show these three definitions as an example in this figure here, where we have this rapidly varying flow, gradually varying flow, and a uniform flow. Also, these open channel flows can be laminar, transitional, or turbulent, depending on the Reynolds number. So these are similar to pipe systems. We can have laminar, transitional, or turbulent flow depending on the Reynolds number, and if Reynolds number is large, we can have turbulent flows. Like here you can see like a example of turbulence. And typically I think there is a Reynolds number more than 10,000 is turbulent in this context, and less than 2,000 is laminar, and in between is something we call transitional. Regime. Okay, so this was kind of an introduction to hydraulic engineering and the terms and the terminology and the way we define these systems, these open channel flow systems. So important thing is we have a fluid depth, which is an important parameter in these systems, in addition to other things like velocity or discharge, which we had before. And the other thing, we are going to look at it later, but the depth of the channel can also change but for now we can assume it's constant, and later on we will take a look at the channels in which their width is also changing. Okay, so now before moving into some details of these hydraulic engineering and open channel flows, I want to talk about a concept which is wave speed, which is very important in this context, okay? Because we need to know the wave speed of the water when we solve these equations, okay? So in order to find the I want to calculate the wave speed for a small magnitude of wave. So consider a single wave of small height, which is delta y shown here, which we also call it a ripple, right? So for example, probably you have seen that when you throw a stone or a rock on a lake, you see that there are some ripples that are kind of formed, and then those ripples are moving with some wave speed, right? With some wave speed, which we show it as c here. And so consider a single wave of that system of where we have a small height, and for example in this context that this wave speed or this wave is moving to right, okay? So this has a small height of delta y, and then it's moving right, and this is the depth of the fluid y, and the depth of the fluid before the wave is reaching to that is y, and the depth of the fluid which after the wave is gone is y plus delta y. So this delta y, because of its height, is gonna move toward the right. Okay, so now I want to find what is the velocity of this wave, or the speed of this wave, based on our governing equations, which are continuity and could be we can use either a momentum equation or Bernoulli equation. Okay. So in order to make this system a little bit easier, I'm going to change my frame of reference. So now, if you are an observer, a stationary observer who is sitting here, okay. So for example, you are sitting here, and then you are looking at this system, okay? So what you see is that this wave is moving to the right, okay? So this is like a non-stationary system that it's moving along the channel. But now I want to make this more simplified to be able to solve this. So what I'm gonna do is I'm gonna assume that you are an observer who is moving along the channel with speed c. So you are actually on the wave, right? Say for example you are surfing, so you are on the wave here, and then you are also moving with speed c along this channel, along this wave, okay? So if you do that, you feel that the wave is stationary, right? Because you are moving with this wave. So you feel that the wave is stationary, and the water here, the fluid here, is coming towards you, right? It's coming towards you, and the water here is going after. So this is how you see this, okay? So this would be the new frame of reference, the new observer in which it is moving with the wave, okay? It's moving with the wave, and so it sees that the wave is constant or is stationary, and it sees that the water here, the fluid here, is coming towards that observer, okay? And the water here is also going after that. So what is seen here is that the velocity is minus c, which is going toward this direction, and the velocity here is going to be minus c plus delta v. So it's not exactly this, right? It can have a different velocity, so I just add that as a delta v, as a difference of the velocity here and here. And the reason there should be a difference in the velocity is to kind of satisfy the continuity equation, right? You have the same velocity here, but you have different area, so your flow rate is not going to be the same. So there should be a difference in the velocity between section 1 and section 2, okay? So that is why I show it with delta V. And now I assume this green control volume, which is the control volume that is actually moving with the fluid, okay? But here, what I see is that the wave is the wave is kind of stationary because I am moving with the wave, and instead the fluid is moving towards me with this speed to this control volume, minus C at this section 2, and minus C plus delta V at section 1. Okay. Now I can write the continuity equation for this selected control volume. So let's write the continuity equation for the selected control volume. So on this section I have minus C, which is the velocity, times Y times the channel width. The channel width is B, okay? So this is gonna be the area. And this is velocity, right? So it's like the discharge, V times A. So minus C times area, which is Y, multiplied by B, which is the area at this section. This is like a 3D, right? So I did not draw the channel width here, but you have to multiply it in order to get the right discharge. So minus C times Y times B equals to the flow rate at here, okay? The flow rate at section 1, which is minus C plus delta V. Again, this is the V at 2. This is V at 1. This is A1 at 1, multiplied by Y plus delta Y times B. So this is A at 2. Okay, so this is like the continuity equation for this system, and if you simplify that, you will get this, because this B is going to cancel with this B. You're going to cancel out, and then you are left with this equation. So you will get this equation, C equals to Y plus delta Y multiplied by delta V over delta Y. So this is a relationship you get for C based on delta Y, delta V, and Y. And then we can enter our assumption of small amplitude waves. So we have in the limit of small amplitude waves where delta Y is much smaller than Y. So delta Y is much smaller than Y because we have a small amplitude, a small height wave. This means that we can just neglect delta Y here in this part, so Y is much bigger than delta Y, and I can just write this C equals to Y times delta V over delta Y, okay? So this is gonna give me the first equation, which is coming from the continuity equation, and we see assumption that we have a small amplitude wave, and now we have found C, which is what we want to find based on delta V, delta Y, and Y. But I want to get rid of delta V and delta Y. So I will write another equation to find a relationship or find an expression for C or waves. So the second equation you can write is either you can write momentum equation or Bernoulli equation. I choose in the book you can see that it's written momentum equation, but I choose to write Bernoulli equation, and the reason I want to do that is because it's a little bit easier. So here we have that relation, which is equation 1, which is coming from the continuity equation. So I write the Bernoulli equation. We can assume that there are no losses. So we have to assume there are no losses if we want to write Bernoulli's equation, because otherwise we have to assume for the like those losses in the system. So we can assume there are no losses to apply Bernoulli's equation along the surface. So I'm going to apply the Bernoulli equation along the surface. So I'm just going to write it down. P2 at section 2 plus 1/2 rho c square is the velocity here, plus rho gy equals to P1 plus 1/2 rho c minus delta v square. So I mean, I just changed it a little bit. It's going to be the same. It's minus c plus delta v. It's going to be the same because we are squaring it, okay? Plus rho g times y plus y, delta y. So this is rho g h, if you remember, the hydrostatic pressure. So one thing is P2 and P1 are in the vicinity of the atmosphere, right? Here, I'm writing it along this surface, right? Along this free surface. Starting from here to here. And then, so we can just assume that they are zero if we are writing this in the gauge pressure. And also, I can, after that, I can cancel all these densities, because this is the water density is constant in your system, right? So this is gonna give me this equation. So I'm gonna get 1/2 c square plus gy equals to 1/2 c minus delta v square plus gy plus delta y. Okay. So I just expand this here. Expand this term here. It's gonna give him 1/2 c square minus 2 times 1/2 c delta v plus 1/2 delta v square plus gy plus g delta y. Okay. So first of all, these two terms are gonna cancel out. 1/2 c square from both sides are gonna cancel out. These two terms are also gonna cancel out, gy and gy. And then I'm going to make another assumption. I'm going to assume that delta v square, because this is like a very small change in the velocity. It's like delta, right? I'm showing it with delta. So it can be like 0.1. You can assume that it's like 0.1, okay? So delta v square is going to be much smaller than delta v, right? Because like 0.1, if you assume delta v is 0.1, so delta v square is going to be 0.01, right? It's like 10 orders of magnitude, 1 order of magnitude smaller than delta v. So in this equation where we have delta v, this term is going to be much larger than this term. So I can just assume delta v square is almost equals to 0, right? Again, just if you want to see why, because delta v is very small, so you can assume that, for example, delta v is 0.1. Just an example, it's not exact, right? And then this is going to give me 0.01, right? So it's much smaller than this, so I can assume it's almost 0. And then I am going to get to this equation. So I have this c delta v, which is this, I wrote it here. I have g delta y equals to g delta y, right? So all the other terms are 0, and I am only left with these two terms here. And this is going to give me delta v over delta y equals to g over c. So this is a new relation, which I can call equation 2, right? And now I put this into here. So I have delta v over delta y. I just write it as g over c. So I put this into equation 1. So c equals to y multiplied by delta v over delta y, where delta v over delta y is g over c. So I get to this equation. So it's gonna give me c squared equals to gy. And in other words, to finally simplify that, c is gonna equal to g square root of gy. And this is what we call the wave speed for small amplitude water waves or any fluid wave, like in an open channel flow. So this is a very important relationship because it shows you can find the velocity of these moving small amplitude waves based just on the depth of your channel, right? If you have the depth of your channel, the velocity of these ripples, these small amplitude waves, for example, when you throw a rock in a river or on a lake, those waves are moving with this speed. If you know the depth of the water there, the wave speed is going to be c equals to square root of gy. Okay, so very simple relationship, but very important. Okay, so now based on this wave speed, the speed of the wave, and also the speed of the water velocity or fluid itself, we can define different regimes, and we can define a very important number in hydraulic engineering, which is Froude number. So when you have waves in moving fluid, so here the fluid was constant, the fluid was not moving, right? The fluid was stationary and it was only the wave that was moving to the right. Let me show it again. So the fluid was constant and it was only the wave that was moving toward the right, to the right. So what if you have also, the fluid is also moving? So in addition to the wave, the fluid itself is also moving with speed v, right? So the fluid itself, like the channel, you can assume that you have a channel, open channel flow. So this channel is also moving, like it has a slope, it also moves, and then you create a wave there, right? So you have both these interactions. So one from the fluid itself and one from the wave. And you want to now, based on this, the relative speed of this fluid and the wave, we can define what is known as Froude number. So you have seen the Froude number definition before. We have defined it before, but this is what it really means. So the Froude number is the ratio of the fluid velocity to the wave speed. So the fluid velocity v over c. So in the previous problem where the fluid velocity was 0, the Froude number is going to be 0, right? But what if the fluid also moves? So then we have this definition for Froude number, which is v over c, which equals to v over a square root of gy. So c is the wave speed, which we found from the previous section. Our previous slide is going to be square root of gy. Okay, so now based on this, the value of Froude number, we can define three important regimes in hydraulic system. If your Froude number is smaller, is less than 1, which means your velocity, the velocity of the fluid, is smaller than the wave speed, which is the square root of gy, then we are in what we call a subcritical regime. So what that means is your velocity of the fluid is small. So say you all have, this is like a, just to give you an idea, you can think that you are here, right? You are moving with the fluid is moving, and then you just create these waves, right? So for example, you can touch the water, or you can like throw a rock here, or like touch the water with your hand, and then you create these waves, right? If the velocity of the fluid is smaller than the velocity of the wave, you would see the waves are going to create something like this. Okay? You would see if the velocity is 0, you will just see some circles, right? The circles with the same center. They will have the same center. But now that because the velocity, the water is also, the fluid is also moving, you will see you will go here. The second time that you make this, because you are also moving, you are here. The third time you are here, right? So this is gonna give you something like this. Okay, this is gonna give you something like this, and shape like this. Okay, and then the second regime is where the velocity of the fluid equals to the wave speed, or square root of gy. This is what we call Froude number equals to 1, and what we call a critical regime. Okay, this is a critical regime in which the velocity of the fluid equals to the wave speed. So in this system, if you produce the waves in this system that is moving with exactly the same speed of the waves, you will see that something like this is gonna occur. So it's like a critical regime. Okay, all the waves will have this something in common here. Okay, and then the third one is when the Froude number is greater than 1, where the velocity of the fluid is greater than the wave speed, which is square root of gy. So this is when Froude number is greater than 1, and we are in a supercritical regime. And then you will have something like this. Okay, you will have a shape of something like this. So this is similar to a Doppler effect, if you remember from your physics, basic physics or elementary physics problems. So these Doppler effects, for example, when just to give you an idea, like when you have a car that is moving towards you, and the car is playing music, very loud music, and or it's better just to talk about maybe the engine sound. So the car's engine sound, you will see that when it reaches to you and then when it goes after you, it has different kind of frequencies, or it has different kind of feeling, right? And that is what we call this Doppler effect, which is something similar to here. Okay, and also very similar, this concept is very similar to all the waves, even when you have speed of sound, or what we call another number, which is Mach number. Okay, a Mach number, you have the velocity of the fluid over the speed of the sound. Here you have the wave speed of the water wave, or small amplitude waves, and in Mach number we have the speed of the sound. And then we have three regimes based on the value of Mach number. Mach greater than 1 is supersonic, Mach equals to 1 is sonic, Mach less than 1 is subsonic regime. And if you know that, maybe you know that most of the airplanes are flowing in the subsonic regime. Okay, and we had like some jets where previously they were flying in the supersonic regime, in which their velocity was greater than the velocity of the sound, and then they have to break this wall, right? This sound wall. So this is the problem with the supersonic jets. So they had, if you remember, Concorde was one of the examples of that, where they have a different nose to break this kind of wall here. So this was kind of an overview of the Froude number, because this is very important in hydraulic engineering context, where flows are going to change from supercritical systems to subcritical, and vice versa, depending on the width of the channel and also the velocity of the channel and other phenomena that we're going to go through it in the next sessions. So in the next sessions, we are going to continue with this hydraulic engineering problem. We are going to talk about energy lines and how we can, and at the end of this, we are going to go through other concepts in the hydraulic, like hydraulic jump and other things. So this was kind of an overview and a brief overview of the hydraulic engineering systems. Okay. Thank you very much, everyone.